Good afternoon, everyone, and thank you very much for coming to our opening. First of all, I'd like to thank those of you who have come a very long distance to be here. David Holmes from Chile, Lynn and Rocco from the US, and many others of you who have come to be part of this opening. And of course, all of you have come from England, which is not an inconsiderable distance to come. I hope your journey was safe up here today. For those of you who have come here to hear about our plans for the Centre for Astrobiology, I hope that in the next hour and a half we'll give you an idea about what we plan to do over the next few years. And for those of you who have no experience or knowledge of astrobiology, I hope we'll give you some knowledge about this subject area and what astrobiology encompasses. For those of you who are here also for the conference, welcome to Edinburgh. It should be an outstanding conference. We have 140 delegates attending the conference. This is the largest astrobiology conference we've had in the UK. It's twice the size of the conference 10 years ago, at which the Astrobiology Society of Britain was founded. So astrobiology, the community in the UK, is ever growing, and we hope it will continue to grow. And we have 2.5 days of excellent science ahead. And this event has sort of turned into a sort of motley half-breed of a UK Centre for Astrobiology opening and a reception for the UK Astrobiology Conference. So thank you to those of you who are here for the conference to come to the opening. So before we continue, I thought it might be worth just saying something very briefly about what astrobiology is. We'll hear about that more in depth from Lynn, who's going to give us a summary of astrobiology. But for those of you who are here who have no knowledge of astrobiology at all and what this area of science is, I thought I'd just put up a couple of slides to explain what astrobiology is and why Edinburgh is a good place to be doing this sort of science. Astrobiology has been defined here at the top. I've just written a definition of astrobiology as the study of the origin, evolution, distribution, and future of life in the universe. So it's a very unambitious science, very well defined. But this basically encapsulates what astrobiology is about, trying to understand life, the phenomenon of life, and how it is spread through the universe. I've grabbed 5 questions there that I think are perhaps some of the most interesting questions in astrobiology. We'll probably hear more about these from Lynn, just to encapsulate what this science is about. First of all, how did life begin? What was the origin of life? Is the Earth special as a place where life originated? Could it have originated elsewhere? And that leads on to a second question in astrobiology, which is probably astrobiology's most potent question, or at least the one that causes the most trouble, I think, in the media, which is, does life exist elsewhere in the universe? But nevertheless, it remains one of astrobiology's most interesting questions, and the one that at least captures the public imagination the most. Is the Earth the only example of an evolutionary experiment, or is this occurring elsewhere? But to assess life elsewhere in the universe, we also have to understand the limits of life. So astrobiology is about looking at the limits of life on Earth and thinking about what the future of life on the Earth is. We know that there's been life on the Earth for 3.5 billion years, or slightly longer than that. And we know that the biosphere probably has about 1 billion years to go before habitability comes to an end on the Earth, or something thereabouts anyway. So what is the future of life on our planet? And then finally, the last question is less of a science question, actually more of a technical question. Can we establish a human presence beyond the Earth? Can we use our knowledge of biology, physics, and astronomy to establish a permanent human settlement on Mars, the Moon, other planetary bodies? We'll come back to that in a while. So astrobiology is really a discipline that sits at the interface between planetary sciences, astronomy, and biological sciences. If you want to study, for example, the origin of life, you need to carry out experiments using biochemical or biological apparatus. So this is a question for biological sciences. If you want to study the habitability of life on Mars or search for life on that planet, then you need to build rovers, of course, and that's a question, a technical question for planetary sciences. If you want to look for life on other planets orbiting distant stars, you need telescopes, and that is, of course, apparatus built by astronomers, so you have to involve astronomers in astrobiology as well. So from the origin of life through to searching for life, looking at habitability in our own solar system, and looking at life on planets orbiting distant stars, we have to involve biologists, planetary sciences, and astronomy. So it really is a very interdisciplinary field that covers all these areas of science. Now, you'll see all sorts of stuff in the media, lots of hand-waving stuff about astrobiology is an exciting new science and it's an emerging new science. All of this is complete nonsense. People have been thinking about life on other planets for a very, very long time. This is a statement by Metrodorus, who is a student of Democritus, who first proposed the atomic theory of matter. And this is what he said almost 2,500 years ago. It would be strange if a single ear of corn grew in a large plain, or there were only one world in the infinite. In other words, if you walk into a cornfield, it would be extremely unusual to find a single ear. You normally find a lot of them in a single field. So it would be very strange if there was a universe with just one Earth and not other Earths. Now, we can argue about the appropriateness of this analogy, and I'm not going to do that here. But nevertheless, the point I want to make is this is a remarkable piece of thinking for someone 2,500 years ago. And it just goes to show that at least in terms, from a philosophical standpoint, astrobiology has its roots in the philosophical schools of ancient Greece. People have been wondering about the plurality of worlds, the multiplicity of Earth-like worlds for a very, very long time, right up to the more modern thoughts about astrobiology. So this is a much more modern statement about the field of exoplanet research, searching for planets orbiting stars, distant stars. In space, there are countless constellations, suns, and planets. We see only the suns because they give light. The planets remain invisible because they're small and dark. And this last statement, which is a nice summary, there are also numberless Earths circling around their suns. This could have been extracted from a public summary from a proposal, say, submitted to NASA or the European Space Agency for exoplanet research. But it was in fact written by Giordano Bruno in 1584 in his book on the infinite universe and worlds. So just a nice demonstration that nothing is new. People have been thinking about astrobiology, even Earth-like planets, for centuries. Bruno, unfortunately, was excommunicated and burnt at the stake in 1600 for his various speculations, a sort of Catholic equivalent of the Nobel Prize, I think. But he was probably the first person to suffer the fate of thinking about astrobiology. He wrote these words in 1583. They were published in 1584. But it turns out that 1583 was an auspicious year for new intellectual activities, because far in the north of Europe, it was the year that a new university was founded in Edinburgh, the University of Edinburgh, founded in 1583 as a college of law. And today, our university is a very diverse university covering all subjects with approximately 30,000 students, covering almost every scientific subject you can think about. But I wanted to say something about why this is a good place to be doing astrobiology. Edinburgh was a university that followed on from the Renaissance into the early years of the Enlightenment. And along with other universities and institutions across Scotland, many of the precepts and ideas that actually underpin modern astrobiology came out of Scotland. And here are just some examples. This is Joseph Black, who elaborated or elucidated the properties of carbon dioxide, a very fundamental gas, a primordial gas found in the atmospheres of terrestrial-type rocky planets. It's very abundant, over 95% in the Martian and Venusian atmosphere, important, of course, in our own planetary atmosphere, and directly linked to climate change and greenhouse gas warming. So understanding the habitability of other worlds often involves an understanding of planetary atmospheric chemistry. Joseph Black was a pioneer in this field. Charles Darwin, who was an undergraduate at this university in medicine, who formulated ideas of evolution, the origin of species, and one might say that at the core of astrobiology is the question, is there a second evolutionary experiment elsewhere in the universe? So we follow on from his ideas in looking for evolution elsewhere. James Hutton, who formulated the ideas of modern geology, came up with ideas for stratigraphy. And of course, it's only during the last few years that stratigraphies on the surface of Mars have been developed based on orbital data and rover data as well. So Hutton's ideas on ancient rocks and stratigraphy now applied to Mars. And James Clerk Maxwell, who formulated the ideas of electromagnetism and the kinetic behavior of gases, essential knowledge for understanding planetary atmospheres and the behavior of other planetary environments. So what we have here is a chemist, a biologist, a geologist, and a physicist. One might say the four cornerstone sciences of astrobiology, pioneers in Scotland who provide the backdrop, I think, the historical backdrop to make this an appropriate place to be doing astrobiology. And if you think that we just sit around gloating over the past, that's not the case. We have some great thinkers amongst us today. This is, of course, Peter Higgs, who came up with some ideas about a subatomic particle. So Scotland is still awash with genius. Now, I wouldn't say that, of course, the Higgs particle necessarily has a direct connection with astrobiology, but if you think about biology as just a type of matter, then, of course, understanding the fundamental properties of matter is the first step to ultimately understanding life. But Edinburgh is a vibrant place for many areas of science that cover the field of astrobiology. And that's why we think that it's appropriate to be setting up the UK Centre for Astrobiology at this university. And in a bit, we'll tell you a little bit more about what our plans are and what we've been doing during the last year since we set this centre up. At this point, I would like to hand over to Leslie Yellowlees, who is Head of College of Science and Engineering and Vice Principal, to say a few words about our centre and the university. Leslie.
Thank you, Charles. That was a great introduction. It's my pleasure indeed to stand up and speak to you here today. I'm Vice Principal and Head of the College of Science and Engineering at Edinburgh. It's a fantastic college to be part of. We love working together. Interdisciplinarity is the very cornerstone of how we work, how we operate. And I think the centres such as this one of astrobiology is indeed what brings together many of our different disciplines. In fact, I think the different disciplines, the boundaries are fraying at the edges, if you want. They're merging very quickly. But we still need the core ideas, the core disciplines of each of those subject areas to bring together in such centres such as this one of astrobiology. Now, I have to say, I listened with some concern to Charles's introduction when he said that astrobiology was not an exciting new science. He fooled me. He assured me that when he came to Edinburgh, this was new, and it was exciting, and that we were going to be proud of this centre, and that it was going to take us to new places and involve many of our colleagues. Which do I believe? What he told me when he was being interviewed? Or what he's told you today? Room for discussion, I think. I have to say we are delighted here at Edinburgh that Charles decided to move to Edinburgh. I think it has taken us in an exciting new direction, and I think that's what being at a university is all about. It's all about enveloping, it's all about embracing new technologies. It's about looking at what we do so well and then taking it on to new things. And then they become the standard things, don't they? And then they evolve on again. So, Charles, I'm delighted you're here, and I'm delighted that the UK Centre for Astrobiology is indeed to be housed here and run here from Edinburgh. But I know it's a collaboration between here, us in Edinburgh, and many other universities throughout the UK, and also perhaps entities from outer space as well need to be involved in this centre. So thank you for being here. Finally, Charles, I think your strained link between Peter Higgs and astrobiology was fitting, because I don't think it was so strained. And I think it is indeed necessary for us to look at ideas from all over science and engineering if we're going to proceed with this Centre for Astrobiology, and it's going to deliver all the exciting things you've promised us. If nothing else, the questions you posed at the beginning, I'm sure, are questions that we've all sat and debated at a dinner table with a glass of wine in hand, and I'm sure we'll get the opportunity tonight, not perhaps at the dinner table, but with the glass of wine later, to debate some of those subjects. And I look forward to engaging that debate with you, and I'm sure in the next couple of days at your conference here, you will engage in far more of that debate. So I welcome you all here to Edinburgh. I welcome you all here to hear about the very start of this UK Centre for Biology. And I hope you will come back and you will engage with us all in the future. So thank you for being here, and I'm now handing over to hear more about astrobiology. So thank you all very much, and have a good evening. Thank you.
Thank you very much, Leslie, and I hope as well that over the coming years we will live up to what we've promised and what you expect from us. It's going to be an exciting few years ahead, and I'm also very happy to be here. Before we talk about what our plans are and what we've done, I want to hand over to Lynn Rothschild to give us an introduction to astrobiology. Lynn did her PhD at Brown University in molecular and cell biology and has been a driving force in astrobiology in the US. She's currently NASA's chief scientist for synthetic biology, and we need to talk about that because there are obvious links to synthetic biology here in Edinburgh. And at Ames, she studied extremophiles, life in the high atmosphere, life in space for many years. She organized the first 3 astrobiology science conferences that occurred in the US, which were really the platform from which astrobiology was launched in the US. So she's been a founder of astrobiology in the US, and I'd like to invite her up here to give us an introduction to astrobiology and what this is all about. Lynn.
That was a tremendously kind introduction, and in fact, your introduction was so good that I really don't need to give my talk, and so I'll be spending the remaining 29 minutes playing my bagpipes for you. So that was actually meant as a threat, not a... let me get this started. And I also wanted to start by getting the unpleasantries out of the way. Are any of Professor Cockell's students in the room? I know I saw Jack back there. I saw at least one. I saw a couple. So the bad news for you is I'm your academic grandmother. What he kindly didn't mention is that I was his postdoc advisor, and I guess I bear some responsibility for the fact that he's done so well in astrobiology. So now that we've gotten all those unpleasantries out of the way, what I'd like to do is spend, I hear, about a half an hour giving you sort of my take on astrobiology. And actually, Charlie, I would say that it's an even older science than back to the Italian Nobels and the ancient Greeks. And in fact, I try to argue in my classes that it's, in fact, one of mankind's oldest sciences. That obviously the first order questions that any living organism has to ask are, what's for lunch and how do you make babies? And after that, our ancestors must have looked up at the sky and looked at the stars, and that's why astronomy is really one of the oldest, if not the oldest, sciences. And they must have wondered very early on how everything around them got there and where they're going. And so it's really a privilege to be able to be part of this, what I call the astrobiology revolution. And it really starts in terms of the scientific revolution with Copernicus. And before then, in terms of mainstream science, and leaving aside the Greeks, which I hate to do because I actually just flew from Greece yesterday, that the physical, the natural world was somehow something special, something supernatural. And it was Copernicus who started putting the heavens and the earth together and bring that physical world, the planetary systems and so on, as part of something that you could study by science. Then Descartes and his followers realized that there were stars that were suns like our own. And so suddenly our sun didn't become so special, and that was part of the natural world. I need hardly mention the Copernican revolution, where we realized that the Earth wasn't actually all that special, that we're simply the third rock from the sun. The Darwinian revolution then took the rest of those revolutions and made them complete by saying the biological world on planet Earth is also part of the natural world. So at that point, we're nothing special. Now, the astrobiology revolution really asks the only last question, and that is the biological world something that is more widespread than what we see on planet Earth? And the jury is certainly still out. You can take bets on it. I gather you told me years ago, Charlie, that Lloyd's of London no longer takes bets on whether there's life on Mars. And so you can figure if they're not putting their money there that there might be a good chance. It's hard to believe that we're alone. We have no proof. So we're in this position that we may or we may not have one last shred of something we can hold on to think of ourselves as special. So what is astrobiology? We got the very nice sort of PowerPoint bulleted version. So I'm going to now give you the soundbite version of what is astrobiology. And that is, where do we come from? And we'll go through each of these in greater detail because it's much richer than it looks perhaps at first glance. And you notice that rather than a map of the United States, I show a micrograph of some cyanobacteria. It's where do we come from in a very, very broad sense. The mirror image is where are we going? What's going to happen in the future? And as was mentioned, it's really the only of the three questions that we're going to have a direct influence on. And in fact, it's probably the only one that's going to have a direct economic impact upon us, short of little green men showing up at Buckingham Palace. And that's the last part, are we alone? And I leave that for last because that's the part that everybody loves. But it's really all part of a package, and that's what's so cool about astrobiology is that it's much broader, and it asks these really profoundly important questions that we have as humans. But I like to just summarize the whole field this way, and I guess it's appropriate in Edinburgh. And so to sort of hammer this home one more time, to give you a flavor for how astrobiology thinking is perhaps a bit different than more traditional disciplinary thinking, here is a phylogenetic tree of all of life, only obviously some of the highlights, not everything. But if you were to go to that core part, close to what we think is the origin of life, you see a lot of organisms that live at very high temperatures. Don't even try to read that. It's just meant as a beautiful visual. So in that center, you see a lot of organisms that live at very high temperatures, what we call thermophiles. And so you could imagine, well, maybe life arose at a very high temperature. And that would be a perfectly reasonable biological explanation. But an astrobiologist would ask, okay, what was also happening at that time? Are there other explanations if we start to marry what was going on in the physical and the geological world as well as the biological record? And what turns out was happening from about 4.2 to 3.8 billion years ago, if you don't mind me saying it in American English, was the late heavy bombardment. Now this was a really, really nasty time for the surface of the Earth. We were pummeled by an onslaught of meteorites. We know this by looking at the cratering record on the moon. It was not a very pleasant time to be on planet Earth. And so once you know that and you realize that these meteorites would have hit the surface of the Earth and heated it up, there's a good chance that what we're seeing by the fact that we have the thermophiles at the center is the result of a bottleneck, as we say in evolutionary biology, so that only the organisms that were able to survive at higher temperatures survived and therefore gave rise to the rest of us. So that's a broader way of thinking about that particular phylogenetic question. And if I can paraphrase the great evolutionary biologist Dobzhansky, who said nothing in modern biology makes sense except in the light of evolution, I would say nothing in evolution makes sense except in the light of astrobiology. So let's get back to these three sound bites and go through each of them in a little bit more detail. So let's start with this, where do we come from? And let's hope this works out. This was a lot of fun last night with the keynote. So the where do we come from, in the beginning, you have to really go all the way back to the Big Bang and the origin of chemicals, because if you don't have atoms, you don't have life. And in fact, at the time of the Big Bang, there was nothing. Once you had the Big Bang, you had some hydrogen, helium, and a little bit of lithium produced. You didn't get the other elements till you had generations of stars and so on. So you can see it's all sort of tied in. Students tend to be taught that chemistry is immortal and physics is immortal. None of these things are immortal. They've all evolved just like biology. And it's this intersection and marrying and interchange over the many billions of years that has led to what we see today. Oh, I didn't mean to leave that as the dinosaurs as the last great thing we see today. In fact, a lot of things have happened more recently. We've had the rise of the astrobiology program, and as Professor Cockell alluded to, this started, actually the word astrobiology started many years ago by the Russians in a slightly different context. The exobiology program at NASA and in various European countries was founded over 50 years ago. We had a 50th anniversary party in Washington about 2 years ago. And this was very much tied in with looking for life elsewhere, starting to send spacecraft to Mars, for example, the Mariner missions that went by Mars looking for the Canale of Lowell, and of course instead they found not a dying Martian civilization, but what really looked like black and white television images, sort of grainy and clearly something that's a dried riverbed rather than a dying Martian civilization. And so we had this program and this interest in exobiology, which actually even in Britain goes further back. I'd highly recommend looking at Richard Proctor, who was a British physicist from the late 19th century, who wrote a book, Worlds Other Than Our Own, which could have been written today except for looking for life on Mercury, which we don't do anymore. Anyway, about 1996, there are a whole confluence of factors. We had an administrator at NASA, Dan Golden, who realized that biology was going to be the future in this coming millennium, which we're in now. On top of it, there was the whole publication of the discovery of the ALH 84001, the Martian meteorite, that was thought to potentially, possibly, maybe have some relics of Martian fossils, and this hit the headlines of the newspapers all over the world. There's sort of a funny story related to that, because it was also during the Republican National Convention, and Dole thought his big trump card was going to be announced that there'd be a cut in taxes if he was elected, and instead what was on the front page of every newspaper in the world was life found on Mars. So it just shows that astrobiology even trumps all the elections. So it was that finding of that, the space missions, Dan Golden's vision that he instructed one of his deputies, Wes Huntress, to help found an astrobiology program that was to be headquartered at NASA Ames, which had been the headquarters for the exobiology program before that. And that's really when the whole thing began to crystallize. In the modern era, the Astrobiology Institute was founded, which is a virtual institute, although again the headquarters are at Ames, which means that the people fixing the webcams and so on are at Ames, and the director's there. And we have many affiliates, both within the United States and then affiliates such as the UK Center for Astrobiology. So that's extremely exciting, having this worldwide network, and it's only a matter of time, I suppose, till it's not just worldwide, but interplanetary network. As Charlie mentioned, the Astrobiology Science Conferences have been going on every other year now for quite some time, and I've always sort of thought of it as the Woodstock of astrobiology, if you don't mind the analogy, that it's sort of where everyone can come together, no matter what your funding program from your home country or whatever, that you can make astrobiology really what it should be. And it really does cover so much of the really exciting research going on. Since then, there have been new journals launched, the International Journal of Astrobiology out of Cambridge University Press, Astrobiology, which comes out of the United States, and many other journals that have been around for quite a while shifted gears so that they had either astrobiology sections or rebranded themselves. The European Space Agency, of course, the British and so on have gotten very involved in astrobiology, although I believe the French still call it exobiology, but I won't make any comments after that. And yes, of course, the UK Center for Astrobiology is one of the highlights, and that's what we're here celebrating today. So there was more after the dinosaurs. So this where do we come from, as I've been sort of alluding to, is much broader question than our biological origins, because you can't discuss our biological origins until you understand where the matter comes from, where the chemistry comes from that allows this, and then the chemistry coming together to form the planetary systems, which then allow for the building blocks of life, which then allow for life. So when you ask where do we come from, it's an incredibly broad interdisciplinary question that, to me, my background actually even before the molecular and cell training was in evolutionary biology, is an enormously liberating discipline to go into. So it really is evolutionary biology writ large. So let me give you a second example of how an astrobiologist might think about some of the questions that actually have influenced life greatly. And I put it to my students, what, in the last 4.6 billion years was the single worst day? Now, maybe some of you, perhaps with a soft spot in your heart for dinosaurs, thinks it was 65 million years ago, or those with a soft spot for the invertebrates, maybe 225 million years ago, the end Permian extinction, or whichever you would like to pick. But my favorite, and I think wins hands down, was the one that occurred about 50 million years after the Earth formed, and that was the lunar forming impact. When we were hit by a planet roughly the size of Mars, some people call it Orpheus, and so once it hit the Earth and merged and threw up a lot of matter that then coalesced into the moon, you had Earth Mach 2. And the reason I'm saying that that was the most important day is because it turns out the moon does more than allow us to write great songs in the evening to, strum on the guitar, play in a jazz band, but it's had an enormous influence on life on Earth. And although the first one that most biologists would say would be, well, it provides a clock with the tides, in fact, the clock would be much more regular if there were no moon and we only had the tides relying on the sun. So in fact, what the big thing, it turns out, is that the moon, which is very large compared to the size of the Earth, stabilizes the obliquity of the Earth. So the angle of the Earth as it goes around its orbital plane, and this helps to stabilize our climate. Poor little Mars only has 2 tiny moons, so it's got what's called a chaotic obliquity, changing its climate dramatically about every 10,000 years, which would be a hard thing for us. And so I think that, when you go out tonight, if you can find the moon, thank it for stabilizing our obliquity, because that's been terribly important. It's had all sorts of other effects as well. My students, I think the favorite one of theirs is that it's slowing the rotational speed of the Earth because there's a frictional interaction. And so the moon goes away from the Earth at about 4+ centimeters a year. This is something that was first calculated by George Darwin, so it's all in the family. But it also slows the rotational speed. So when life arose, day length was about 16 hours. It's now 24 hours. It won't, for the students in the room, it's not going to help you before your final exams. It's not going that fast. But it is an interesting thing to note, and that when life arose, photosynthesis, day length may have been very, very different and much affected. In fact, I would argue that because day length was so much shorter, it may have helped to compensate for the higher ultraviolet flux. Of course, the moon is important for space exploration. It's a big, fat target out there. It only takes about 4 days. Apparently, I've already been quoted in the media by saying you only need to pack a few peanut butter sandwiches to get there. This did not help with any raises. Anyway, so that just sort of gives you an idea that here is this lifeless body that's always been lifeless, and yet I would argue it's had a profound influence on the Earth, and I won't go through all the arguments because I don't have the time, but I have argued elsewhere that in fact if we had no moon, that we as humans would be very unlikely to be here, that there would well be aquatic organisms, but not terrestrial organisms. And sort of the interesting thing is that if you look at the very last few sentences of The Origin of Species, so well known, there's grandeur in this view of life, with several powers having been originally breathed into few forms or into one, and that whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms, most beautiful and most wonderful, have been and are being evolved. In some ways, that's an astrobiology finish there, that there's an interaction between evolution and the physical environment. So that's the where do we come from? How do we get the diversity of life on Earth? What are its limits? Is this in any way predictable? What's the interaction between evolution and the physical environment? And we could spend great amounts of time on any one of them. So now let's flip to this mirror image. Where are we going? What's going to happen in the future? This is something that's the Earth is going to change, the solar system's going to change. Just because we're here doesn't mean the moon has stopped going away from the Earth, that the sun hasn't stopped burning, or that eventually we're not going to run into the Andromeda galaxy unless we actually go in there and intervene. So all sorts of things are happening in the future around us. And what's going to be very interesting and important to us is what the response of life, including humans, is to this change. And this is going to include, no doubt, terrestrial life moving beyond its planet of origin. And we might even look at the fate of the universe. This is actually the most depressing slide that I ever show, and I give a lot of talks, but this is it. This is the most depressing one. This is what's going to happen over the next 7 billion years if we don't do anything about it. You know, we've got ice ages and supercontinents, the death of plants and so on. I have to add that I was in a documentary a few years ago, felicitously named Death of Planet Earth. What a wonderful title. Anyway, it was done by a British group, as many of these are, and with an 8-hour time difference to California. I don't know if you know that. Most of them just, they put then US voiceovers, but they're British groups. So they're very, very nice young lady who was a production assistant, and she'd call me at like 7 in the morning and say, "Good morning, Dr. Rothschild. Could you tell me again what year all plants are going extinct?" I mean, this went on, and I was so depressing. And so then we'd go through a couple of days of filming, and, you know, you talk about when the oceans are all going to evaporate, and the last extremophile, you know, puts out his last cigarette, and they all go. And I finally realized that I couldn't spend the rest of my life angsting over this, that you have to imagine that we're somewhere between a Greek tragedy where we can start to see this roadmap for the future and something like A Christmas Carol where we say in the morning, yes, we can do something about it. So I must say I'm fairly optimistic that our descendants will be able to do something about it. Whether it's something like terraforming Mars, here's a cartoon of Mars today, and there it is when you want to buy your beachfront property, you can already see where to place the golf course and so on. So it's going to be marvelous when we're there. And other, you know, possibilities abound. I've been deliriously happy ever since I discovered that there are planets around solar remnants, something that's been known for over 20 years. And so, in fact, although our own star is going to become a red giant, eventually it will become a white dwarf. And the good news is once it's a white dwarf, we're good for basically forever, you know, like tens of billions of years. So maybe all we have to do is move the Earth out, sit out this period of being a red giant and come back. You know, I don't know. I'm sure our offspring will figure out something. You laugh. I once talked to some venture capitalists in California, and one rather shaken man came up to me during the break and asked if we should be starting a hedge fund. Anyway, we won't go into that. But seriously, these are all things that will happen if we don't do anything about it eventually. And they will be things that we'll be thinking about in the future, our descendants will. Which brings us to the Are We Alone, which is the really fun one. And this really boils down to, are we the only life form in the entire universe ever and ever? And then beyond that, or I should say maybe beyond that's the wrong word as microbiologist, but a separate question is there intelligent life? And I gather that this is a room full of fellow scientists so that you know that the big gap is actually between non-living and living, not between a microbe and an intelligent creature. This is, you know, completely reversed from what the general public thinks. But certainly once we have life, you know, the sky's the limit, literally. And this is one that also has enormous ethical implications, which I suspect that Chris McKay will talk about tonight. So this is the one that I would argue that since the dawn of mankind, we've wondered whether we're alone. But the big difference between people who've wondered about it before and even Bruno and all these other wonderful people is that we now have the technology to go out and start to actually answer these questions in a scientific way. The reason it's now is because of this discovery of extrasolar planets. I believe there's going to be a big Kepler announcement today or tomorrow. I don't know if you've heard it already. We've got, you know, again, 8 hours on the Californians right now. Huge number of extrasolar planets. Before in the olden days, like 5 or 6 years ago, we knew of, you know, 10, 20, and then it was 60 and 100 and 200, and now we're getting announcements 1,000 or more at a time. It's unbelievable. So the discovery of extrasolar planets, the missions to go to places within our own solar system and just beyond, the huge, huge advances in molecular biology. I remember as a student sitting around a table discussing microbial evolution, and at the end of looking at a lot of ultrastructures and trying to pick out the, you know, flagellar hairs and trying to divine what they meant, you'd finish by saying, of course, we'll never know. And here it is only a decade or so later, and now we have much greater level of certainty because of modern molecular biology. And finally, we now know so much more about life in extreme environments, about organisms that live at temperature extremes from well below freezing to well above the boiling temperature of water, pH from 0 to 12.5 or so, chemical extremes, extremes of salinity, radiation, and oxygen I add there as well, because playing with oxygen, being an aerobic creature like we are, is an extremely dangerous lifestyle, particularly when you start to think about all those radicals somewhere between oxygen and water. The hydroxyl radical, and on and on and on. And this is a very, very dangerous strategy. I'm not recommending that anyone stop breathing in this room. I'm only pointing out that we qualify as extremophiles as well. Now, studying these organisms that live in extreme environments is extremely, extremely important for astrobiology, because that gives us some kind of minimum envelope for life in the universe. So if we go to someplace like Venus and we see a boiling battery acid-filled sort of hot spring, we don't immediately turn up our noses and, you know, wave back and say, Houston, you know, beam me home, or I guess Scotty, beam me home would be the correct thing here. You would say, well, you know, we found some organisms in Yellowstone, or I'm trying to think some of the places that Charlie and I have been to together, the North Island of New Zealand or whatever, that live in exactly those conditions. So it doesn't mean that those organisms are there, but it just means that there is nothing about these physical and chemical environments that preclude life. So that's what I mean, that life on Earth gives us a minimum envelope for studying life elsewhere. So where should we look? NASA's been taking the simple path of following the water. I firmly believe that Titan, this marvelous moon of Saturn, which does not have liquid water, at least on the surface, but is full of hydrocarbons, has been put there specifically to test our faith in liquid water as a solvent. But besides Titan, we generally look for liquid water. It's a marvelous solvent. It's all over the place. Hydrogen is by far the most common element in the universe, and oxygen's up there, I think, is number 3, so lots and lots and lots of water. It's got great chemical properties, including the fact that it floats when it's solid, which is very unusual. That allows you to have a gin and tonic with the ice cubes floating on the top. But even more important for astrobiology, it allows you to have a moon like Enceladus, excuse me, or Europa, that has an ice-covered surface with liquid water underneath. This just reminds you of our neighborhood. Mercury, unfortunately, is a no-go for astrobiology. Whatever Richard Proctor had to say. Venus is sort of a sad case in that it was very similar to the Earth, probably for its first 3.5 to potentially 4 billion years ago. But it was something very bad happened. And that is that as the sun heated up, the liquid water that was presumably on the surface was heated up and went into steam. Now, water vapor is a very good greenhouse gas. And so what you ended up with was a feedback mechanism and a runaway greenhouse effect. And the result is that poor Venus today has the hottest planetary surface in our entire solar system, hotter than Mercury. In fact, the story is that the Russians sent several lead busts of Lenin to the surface of Venus. And so today there are several little Lenin puddles on the surface of Venus. So this is not a place that you would ever expect life today. But there is some thought dating back to Carl Sagan, 1967, that there could have been, in fact, there should have been life evolving on the surface of Venus when it was much more similar to the Earth. And that perhaps as this runaway greenhouse took over, that these organisms went into the cloud layer where there is plenty of water vapor and the temperatures are much more familiar to us than the pH and so on. So still potential for life in the clouds above Venus, even better chance for life early on Venus. Earth, the third rock from the sun, is of course infested with life. I don't even need to tell you that. Mars is an open question. It too should have been more similar to the early Earth, but being fairly tiny, it lost its atmosphere much earlier. And so it's sort of the opposite of Venus. It lost its atmosphere and became cold and dry. Again, still potential for life there. It's close, and that's why we keep hammering at it every few years. Excuse me. But at this point, no actual evidence. Sorry, Chuck, do you have any water? I'm sorry about that. this was what we thought was all she wrote up to a few years ago. I'm sorry, I'm sort of fighting a cold here. So that should have been well out of where we would consider the habitable zone. But it turns out that there's some moons of Jupiter, the Galilean moons, that are extremely bright. They have a very high albedo, which is indicative of ice. And that was all very nice, but you'd figure, well, how could you warm up beneath the surface of the ice layer enough to have liquid water since it was so far from the sun? And then we realized that there was tidal flexing going on. So this provided a way for a body that was well beyond what should have been a habitable area to have liquid water and therefore potentially habitable, particularly since we now have images from Galileo. We have various other sorts of data that indicate that they're organic molecules. Once you have organics and water, indicative of life. Potentially the same thing with Ganymede, which is another one of these Galilean moons of Jupiter. Enceladus, one of these little moons of Saturn, we know for a fact there's liquid water beneath the ice-covered surface because we can see it shooting out. You'll hear a lot more about all these tonight, I'm sure, from Chris. There's Titan, also around Saturn, which is a different situation. It's lots and lots of hydrocarbons, no liquid water on the surface. Potentially, we could go beyond that. We see all these trans-Neptunian objects, some of which are very bright, have this very high albedo. There may be some potential mechanism for heating beneath the surface so that you have liquids. There's absolutely no evidence one way or the other, even that potential for little former planet Pluto. So I've learned in astrobiology not to be too definitive, because as soon as you are, there's some new discovery and you have to eat your words. And of course, then there's beyond our own solar system. Kepler, which I alluded to earlier, is this marvelous mission that we're very proud of because it was launched, it was conceived and launched out of NASA Ames. It's managed by NASA Ames, where I work. And what it does is search this small part of the Milky Way galaxy by doing something incredibly stupid, and that's why I consider it an incredibly brilliant mission. All it does all day long is stare at 150,000 stars. And at some point, it turns around, beams some data back to Earth, and then stares again. And it stares and it stares. And what it's looking for is little tiny bits of dimming by stars in a periodic way. And that indicates that they're planets transiting. So obviously, you have to be in the right orientation. It's only been up looking for a few years, so you have to have the planets transiting at a higher frequency, or at least be lucky that you've seen it. And so, you know, yes, there are all sorts of problems. But that being said, I want to show you this terrific image that I got down from the web. This was made over a year ago. These are not the planets that were found by Kepler. These are the planetary systems. If we had all the planets, I wouldn't be able to get them all on my screen. So these were the planetary systems that were discovered over a year ago. It's grown much more since then. This is just unbelievable, rich treasure trove of data. And as I say, I'm pretty sure that there's going to be a big announcement this week and possibly today. So you are left actually with not just scientific questions, but philosophical questions. If we are one of many life forms, what is our place in the universe? What should be our relationship to other forms? Does it matter if they're intelligent or not? They, of course, may have different definitions of life than we have. They may not consider us intelligent or even alive. But what about the converse? What if we actually are alone? And it turns out that after this big march of the revolutions, where we have given away our special status as a solar system, as a sun, as a planet, as a life form, that in fact we reverse just a little bit and say, you know what, we really are special. We won't know the answer to that one within our lifetimes, because it's going to take a lot of searching before we give up. We may know that we're not alone within our lifetimes, but we won't know if we are alone. But if we are, then that also leaves various philosophical and potentially ethical implications, looking and saying, gee, we really are something special that we needn't fret. So I wanted to close with a little plug-in here for synthetic biology, that we've talked a lot about things that you can glean from observational science. whether it be astronomy, biology, chemistry, or whatever. But there's also an experimental way that you can go about this. And this is where the synthetic biology comes in. Now, synthetic biology has all sorts of definitions. Design and construction of new biological functions and systems not found in nature. You can throw in all the big buzzwords, emerging, innovative, game-changing, you know, blah, 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 all these things that look great in the reports. In fact, Richard Feynman said, what I cannot create, I do not understand, and that's really, usually uses the poster quote for synthetic biology. But in a lot of ways, the simplest way to think about it is an analogy with chemistry. For millennia, we did descriptive chemistry, and then 100 or so years ago, we started doing experimental and synthetic chemistry. And we really have done the same thing with life. For millennia, we have done descriptive biology, and now we're switching over to doing synthetic biology. So it really subsumes a lot of the genetic engineering that's been going on over the last few decades. So on Earth, we're using this to put new metabolic capabilities and so on in organisms. The applications are numerous, from material science, manufacturing, environmental control, biofuels, food, pharmaceuticals. These are already getting to be very big industries and growing very quickly. And in fact, the UK is one of the main centers for synthetic biology in the world. And Edinburgh is one of the main centers within the UK, so that's a very interesting link right there. But what we're suggesting is there's no reason not to take synthetic biology and apply that not just to some of these other questions of astrobiology, like where do we come from, but the perhaps more future-oriented ones, like where are we going? So if we look back, we can play with making different genetic codes. There's no reason that we have to be satisfied with using GACT for our DNA. We have people like Steve Benner in Florida, who's made a couple of extra nucleotides. So he says there's no reason you shouldn't use GACT-ZP DNA. Phil Hulliger's group at the MRC had a really brilliant paper out a little bit less than a year ago on xNAs. They call them xenonucleic acids, both xenoRNAs and xenodNAs, and we're able to take the DNA as a template, and you don't really use the word transcribe, but you know what I mean. Transcribe it into these xNAs and then reverse transcribe it back to DNA, which is just really brilliant. There are people who are working on alternate biochemistries. Everyone in this room uses left-handed amino acids and right-handed sugars. Why not make a mirror world, a through-the-looking-glass world where you're using left-handed sugars and right-handed amino acids? There's no reason not to, and then you would know which is us and which is them. You wouldn't have the same kind of potential for disease or cross-reactivity. You could have alternate cellular acellular systems, new types of organelles. There have been people who have started to make organelles out of microfluidics and proteins. So, I mean, this is the equivalent of an artificial heart, but at a subcellular level. I mean, unbelievable stuff. Or take given components like a ribosome and totally reprogram them. I have some colleagues at Northwestern University near Chicago who say, look, a ribosome is just a polymerization machine. So instead of polymerizing amino acids, why not take it and reprogram it to polymerize something to make, say, plastics or nylons or something else? I've seen people suggest making fibers that you could use for carpets using biology. It's, you know, this is the dawning of an era of a lot of very strange things. And if this sounds so far out, all I can say is, every time I say it's impossible, you see a publication within 6 months or a year saying that someone's achieved it. This is a really incredibly rapid field. So I'll just end with one or two projects that our lab has been doing. We talked about looking at life in extreme environments as a way to get an idea of what the envelope for life would be. So I have a group of students last year who started asking the question, could we make artificial extremophiles? They called this project the Hell Cell, which I thought was very, very evocative. And in fact, in the course of the summer, which has now been continued on as an ongoing project, they were able to take E. coli, which is sort of the workhorse bacterium in molecular biology, and make it more resistant to heat, to cold, to radiation, to desiccation, to salinity, every one of them. I mean, at the beginning of the summer, I was tempted to say, this is impossible, don't bother doing it, this is 3 PhD theses if you're lucky, and in fact, every one of their projects worked last summer. It was unbelievable. This is why I no longer say no or it's impossible. Absolutely unbelievable stuff. So this helps to expand this minimum envelope for life. But the final thing is this going forward is that we believe firmly that synthetic biology is what's going to enable the sort of human settlement that Charlie alluded to before. And if you look at what is required for human settlement off the planet Earth, to Mars or an asteroid or whatever, you have to really have a lot of infrastructure there. Transportation, habitat, life support, power, heat, light, radiation protection. I talk a lot to various military organizations, and they say, oh, well, it's so difficult to, you know, go up into Afghanistan or whatever. And I just laugh. I say, look, you've got oxygen and gravity. We don't even have that. You know, you're lucky. I mean, you basically are there with a really foreign environment. And on top of it, you have some major challenges. The big one is upmass. In other words, the amount of mass that you're lofting into space. And that is related very intimately to cost. The number that has been bandied around for years is that it costs about $10,000, I'm sorry, you have to do the math into pounds, to launch 1 can of Coke into low Earth orbit. Now that's low Earth orbit, that's not even getting to Mars. It's a very, very expensive can of Coke. And so you want to be very circumspect of what you actually want to launch and instead see what you can make on site. On top of it, you have to worry about storing these materials. It's going to take you at least 6 months to get there, and flexibility once you're there, because you can't really call Amazon.com and have stuff delivered the next day. You have to be prepared for anything. So what's the big idea here? So I'm just going to leave you with a few teasers. Well, for millennia, we've used biology to do chemistry for us on the Earth. We use biology to make yogurt and beer and certainly the first half of whiskey and, you know, on and on and on, not to mention wool and cotton and, you know, wood, you name it, we've used biology to do this chemistry for us. There's no reason to think that as we go forth on planet Earth that we shouldn't continue to use biology to do this chemistry. Where are we going to get the raw materials? We may take some from the Earth, particularly ones that are hard to find elsewhere, but many of them can no doubt be acquired from an asteroid in transit, potentially for the place you land, either an asteroid, a comet, or Mars or the Moon. You may be able to acquire some metals and minerals from the surface, but even more than that, if you can get water at this location and you can get organic carbon, as you would be expected to get at least in a carbonaceous meteorite or asteroid, and CO2, which allows you to do photosynthesis, you should be able to produce a certain amount of your biomass from locally sourced materials. And then you can go ahead and produce food, nutritional supplements, drugs, fuels, and so on as you feed this material into a bioreactor, including polymers and fibers for clothes, heat, and so on. We may use these synthetically altered organisms to make materials for construction. For example, a project that's been going on in my lab for the last 2.5 years is altering microbes to glue together materials from the Martian regolith. Obviously, we don't have materials in Martian regolith, so we use a simulant. But you can literally make bricks. And once you have a brick, you can really make anything from the Colosseum to New York City. You know, you have these small modular construction units that would be prohibitively expensive to send with you. But if you can make them locally, the conceit being with just a tiny test tube of microbes that have then been grown with this locally sourced water and CO2 and so on, you can build these enormous structures with almost no upmass. You could create these alternate biochemistries that I suggested before, so you have this group of organisms that would not cross-react with you, that could go out there and do your bidding. So the future is very strange and very wonderful. The near future of what we're starting to do with the synthetic biology and where we are with the space missions is not so distant. It's now, it's immediate, and that's why I kept saying Kepler announcement today, UK Centre of Astrobiology today, 2 big, red letter days in the history of the known universe, no doubt. Lots of exciting things going on, and so I congratulate the University of Edinburgh not only for admitting both my children who are here studying biology, I'll put that plug in, but also for having the foresight to open this center, which is really a marvelous thing, and even better to put it under the wonderful leadership of Dr. Kakel. So thank you very much.
Thank you very much, Lynn, for this very eloquent, excellent, accessible introduction to astrobiology. So Lynn has provided us with some of the breadth of what astrobiology is about. And now what I want to do is talk specifically about the UK Centre for Astrobiology and what we've been up to and what our plans are for the future. This is a young centre. We're 1 year old, and I'm not going to say much about my own research group. My students and postdocs are in the audience, and if anyone wants to talk about life in extremes, we're always very excited and happy to talk about that. But I want to talk specifically about the projects that we've implemented in the last year that are designed to enhance national capability in astrobiology and improve our ability to do this science in the UK. So just to say something about the history, Leslie already said that this began when I was asked to interview at Edinburgh. And they asked me, what am I going to do here? And I said, well, I'm going to set up a centre for astrobiology. And no one seemed to blink their eyelids. So I thought, okay, that's fine, I'll do that. So I came here, and it's a logical place to do it. I've said something about the history, but the present day science at Edinburgh also makes this a very logical place. Edinburgh is a home for the Centre for Science at Extreme Conditions that studies extreme conditions and effects on physical materials. It has a very strong synthetic biology section here, group that links, I think, to what Lynn said at NASA. Also, these groups that I've listed here, all of whom have some links with astrobiology. In fact, Kate McPhee should take a lot of the credit for this whole centre. She was the one who came along one day and suggested I might take an interest in Edinburgh. So it all really began then, and she's working on protein biochemistry. We have these other groups here. So there's critical mass at Edinburgh. It seemed like a good place to set up a centre to carry on this science. So I'm going to start off with our mission statement. This is our mission statement that sort of underpins everything that we do, that circumscribes the sorts of things we get involved with. And it just says the mission of the UK Centre for Astrobiology is to advance our understanding of molecules and life in extreme environments on the Earth and beyond. It does this by a combination of theoretical, laboratory, field, and mission approaches, and we apply this knowledge to improving the quality of life on Earth and developing space exploration as 2 mutually enhancing objectives. This is our website here. We recently became affiliated with the NASA Astrobiology Institute. We're one of 14 organizations around the world to be affiliated with the NAI. And I should say, intriguingly, this is the only country that has 2 affiliate nodes with the NASA Astrobiology Institute. The Astrobiology Society of Britain is also affiliated to NAI. So either they're impressed by us or just completely confused. I think probably some element of the latter. But this allows us to create connections with NASA projects. And I'll provide some examples of how we have used this affiliation to build new projects that will advance astrobiology in the UK and abroad. So a couple of things to mention here about this mission statement. First of all, we don't recognize a separation between environmental problems and space exploration. It's all about building human communities in the universe. It doesn't really matter whether it's on the Earth, Moon, or Mars. That's a small technical matter. It's about creating sustainable human communities. So we regard this as 2 prongs of the same challenge, improving the quality of life on Earth and establishing a permanent human presence beyond the Earth, are really one and the same objective for our civilization. And we've also chosen to focus on molecules and life in extremes. And you might wonder why that particular focus to the center. If you look at some of the things that Lynn has talked about in astrobiology, a lot of them come back to understanding molecules and life in extremes. If you want to assess habitability, the possibility of life on other planets, you need to know something about life on Earth. What are the limits of life on Earth, and how can we use that knowledge to improve our knowledge of habitability elsewhere? If you want to search for life on exoplanets orbiting distant stars, you need to know what sort of gases microbes produce. To do that, you have to look at microbes on the Earth. So that comes back to molecules and life in extremes. If you want to understand life on early Earth, you can't build a time machine. You can certainly look in the rock record, and that'll tell you something about life on early Earth. But another very good way of understanding life on early Earth is to look at the limits of life on present-day Earth and get some idea about how life might have adapted to extreme conditions on the early Earth. So that comes back to this as well. And then finally, if you're going to establish a permanent human presence beyond the Earth, you need to understand something about biology. Lynn spoke about synthetic biology, using biology to improve the prospects of the establishment of humans beyond the Earth. So all of these things come back to molecules and life in extremes, and I like to think of this as the empirical core of astrobiology. This is the thing we can actually go into a lab and do and apply to these other areas of astrobiology. And that's the reason why we've chosen to build a center that focuses on this phrase here, molecules and life in extreme environments, and that's what we're going to do. So this is all very nice. This is all the sort of mission statements, all this modern stuff you have to have, very hand-waving. What's the substance behind this on what we're doing to implement these ideas and actually advance astrobiology? Well, we implement our vision, our mission statement, with 4 objectives. We have 2 science objectives, a technology objective, and an education objective. Our 2 science objectives, O1 and O2, are to advance our understanding of how molecules and organisms respond and adapt to extreme environments. O2 is apply this knowledge to advancing our understanding of the habitability of other worlds and the search for extraterrestrial life. And then we have a technology objective, O3, improve the translation of astrobiology technologies designed for the exploration of space to solving urgent environmental and social challenges on the Earth. And then finally, our 4th objective, use astrobiology to advance public education in science. That's our education objective. So these are our 4 objectives, and these define what we get involved with and allow us to focus our projects and activities. And for the rest of this talk, I want to go through each of these 4 objectives and talk about the projects that we've implemented. This is somewhat of a review of what we're up to, but also an advertisement for the community. So I'd like to, before I talk about these things, simply say that if you know of people who might have an interest in what I'm about to say, please get them in contact with us, because the idea of these projects is to advance UK astrobiology. So let's start with O1, advancing our understanding of how molecules and organisms respond and adapt to extreme environments. One way in which you can advance UK astrobiology in this area is to create facilities in extreme environments that will allow people to get a better understanding of how life adapts to extreme conditions. And so over the last year, we've been building up a new international facility called BISSL, the Boulby International Subsurface Astrobiology Lab. This is the world's first permanent deep subsurface astrobiology lab, and it's located in a potash mine, a salt mine that's 1 kilometer deep, that's run by Cleveland Potash. And Dave McCluskey and Dave Pybus are here, and I'd like to thank them for their support for this initiative. This is where it is. It's just north of Whitby. This is CPL. It's an active potash mine. And it's been the location of a dark matter laboratory for over 10 years. This is the Palmer Lab, 1 kilometer depth underneath this salt. It's a very quiet place in terms of radiation. The rock above here cuts out the radiation, and physicists have been using this lab to do dark matter research. And a year ago, when we were setting up the center, we looked at this lab and we started drooling, and we started thinking this would be good for an astrobiology lab. So we went to CPL with a proposal to build an astrobiology lab here. And we've since been funded very kindly by the STFC Futures Program. Catherine Ewart, thank you very much for that support, to equip this laboratory. Here's the area of the laboratory that's being turned into an astrobiology laboratory. Why are we interested in building an astrobiology lab 1 kilometer underground? Well, the reason is that it's full of very fascinating habitats and environments like this. This is a stream flowing through pure salt, 1 kilometer deep underground in complete darkness. And we want to know what sort of life lives in complete darkness 1 kilometer underground in these very salty environments. Why would anyone have an interest in doing that? Well, these are the sorts of scientific areas that can be advanced by studying life in the deep subsurface. Depending upon whose papers you read, about between 40 and 90% of the biomass of life on Earth is underground. That's where most of life on our planet is, beneath the surface. If you want to understand life on Earth, you have to go underground. We're easily distracted by all these large organisms on the surface of the planet, but a lot of the biogeochemistry, the cycling of elements, is occurring underground. So understanding subsurface microbiology is a very important area of science. These subsurface microbes are important in cycling sulfur, carbon, nitrogen, other elements that are crucial for the biosphere. And so we want to understand biogeochemistry in the deep subsurface, how the microbes contribute to the flux of nutrients and elements through our crust and through our biosphere. This is a lab, as I said, that's been used by the dark matter researchers because it's low in radiation. But as Lynn said, radiation is very important for life as well. And this represents an important opportunity to see what happens to life when you cut out radiation, when you take it to below background levels of radiation. So we've started doing experiments in the deep subsurface to look at what happens when you remove the background levels of cosmic radiation to the behavior of life. And of course, the study of ancient life. This mine is built in Permian salt. It's the remains of a 250-million-year-old ocean, the Zechstein Sea, that existed in Central Europe during the Permian. And these tunnels through the mine are through this ancient salt deposits. So we can start to look at ancient life in these salts, in these Permian salt environments. So these are just 4 areas of science that we think can be advanced by using a permanent subsurface laboratory where we can grow microorganisms, flow liquid through the lab into the outside environment, and study how microorganisms behave. So this laboratory is now being equipped. In fact, the first shipment of equipment arrived last week. And the only point I want to make is this facility is now available. And please get in contact with us, and we are going to start coordinating a science program to look at life in the deep subsurface and understand how life survives in deep salts. Now, it turns out that salts are very important for understanding extraterrestrial environments. So moving on to the second objective, applying this knowledge to understanding the habitability of other worlds and the search for extraterrestrial life. There's a lot of salts on Mars. This is about 150 kilometers across, and these are putative brine seeps possibly flowing out from the subsurface of Mars. Now, whether they are or not is a matter of debate, but we do know that there's lots of salts on Mars, lots of sulfates, possibly calcium chloride, other types of salts as well. If you want to understand the habitability of Mars and its subsurface, you need to know something about life in salty environments and possibly in deep subsurface salts. So the Boulby laboratory gives us access to these really interesting deep subsurface environments where you've got microbes living in salty environments in complete darkness where there's no sunlight for them to get energy from photosynthesis. So by looking in Boulby, we might get ideas about the habitability and the geochemistry of environments on Mars and whether these were ever inhabited. And even if they weren't, what's the geochemistry that's going on here? We can use these analog environments on Earth to understand Mars. So Bissell will also be used as a facility for understanding life on Mars. So moving on with this objective, one of the things we really want to do is not just build labs in places that are interesting for extreme environments that are like Mars, but recreate these environments in the laboratory. So we've been spending the last year developing state-of-the-art planetary simulation facilities to improve our ability to simulate Martian conditions. And as has already been alluded to, one of the, I think, remarkable discoveries on Mars, at least during the last few decades, although it goes back to the Viking landers, is the discovery that in the ancient history of Mars, there were large quantities of liquid water. This is a valley network. This is a vintage Viking orbiter image, and a more recent image from the Curiosity rover showing these conglomerated rocks, which suggest at least persistent bodies of liquid water on the surface of Mars. Now, most Mars simulation chambers that exist in the UK today are essentially glorified vacuum chambers. You put your experiment in, you reduce the atmospheric pressure, you recreate a Martian environment, and then you do your experiment. And we've been hard at work creating a new type of Mars simulation chamber from scratch that will allow us to do some novel things. This is built so that we can do accurate scientific replication within this planetary simulation facility and also collect samples from inside the Mars simulation chamber whilst we're carrying out experiments. And there are several things that we wanted to do in the light of new information coming back from Mars. We wanted to develop the capacity for studying flow-through to look at water-rock interactions over many months so we could study the habitability of ancient geochemical environments on Mars. So this is designed to allow for the flow of simulated Martian liquids through these sample containers that will allow us to study water-rock interactions under simulated Martian conditions for many months. We wanted to collect samples during the Mars simulations. We don't have to draw down the whole atmospheric pressure and then bring it back up to Earth atmosphere to get our samples out. So we've devised a series of valves that allow us to go into our experimental replicates and collect samples from inside the Mars simulation chamber during the experiment without changing the conditions inside. We also wanted to flow unpleasant acidic solutions through this Mars simulation chamber. We know that in one period of Martian history, when there was less water on the surface of Mars, sulfur dioxide was mixed with Martian water, and there was acid weathering on the surface of Mars. And we've designed this thing with vacuum pumps and other connections that are resistant to acid conditions. So we'll be able to simulate acid weathering on the surface of Mars. And this is all the work of Derek Martin, who's been working on this for the last year. We can do anaerobic manipulations in here. We want to look at anaerobic microbes. There's not much oxygen on Mars, so we can do manipulations in here to look at anaerobic conditions, actually while the experiment is occurring. And we've also got sophisticated gas analysis that will allow us to look at gases being produced from these sample chambers. So this chamber will allow us to study life on past and present Martian geochemistry, to look at the habitability of Mars, whether these ancient environments could have sustained life, and also to investigate biomolecule survival on Mars in its early history. And having now got this experience, this hard-won experience over the last year, we hope that UKCA can become a focus of technical expertise in building planetary simulation facilities. But one reason to tell you about this is to advertise it. If you know of anyone who's got compelling science questions that could do with these capacities or that they can't do in other facilities, please get them to get in contact with us. And we can make this facility available. Full economic costing, of course, but it is available to anyone who's interested in collaborating on Mars simulation experiments. And over the coming years, we hope to upgrade this and improve it. And this was very kindly supported by funding from the University of Edinburgh when I first came here. So moving on now to Objective 03. One of the things that we want to do is not just create capacity for doing science in the UK, but improve the translation of astrobiology technologies designed for the exploration of space to solving urgent environmental and social challenges on the Earth. And I just want to talk about a couple of those projects that, again, we would like to widen community involvement with in developing astrobiology. So one of the challenges, or two of the challenges that our civilization currently faces are establishing a permanent human presence beyond the Earth and trying to find ways to extract minerals safely and effectively from the crust in an ever more resource-depleted world and in a society that requires more and more elements to feed this technology-intensive civilization that we've developed. And it turns out that these two challenges have the same sort of technological problems behind them. So I've just written a statement here to make this easier to understand. A major challenge in space exploration and mining is building instrumentation and robots that are miniaturized to reduce mass and energy requirements and can operate in extreme environments. So if you want to characterize, for example, minerals on the surface of Mars, you want a small instrument because you don't want to have to launch a large mass into space. You want it to have a small energy requirement because, of course, you don't want to have large batteries or nuclear power units, or at least you want to be able to minimize those things. And it needs to be able to operate in extreme environments because Mars is a very extreme environment. And these are exactly the same specifications as mining companies require. If you want to extract potash from the deep subsurface, which is CPL here, and you want to characterize the minerals, you want a small instrument that's not going to get in the way of your mining operations. You want to minimize energy requirements because you don't want to have to keep running large power cables down your mine. If you can minimize energy, you can minimize logistical problems and thereby make your operation more financially competitive. And of course, mines are very extreme environments. So we've got two challenges, space exploration and mining, that face the same technological problems. And we recognized this when we set up this center. And we thought this is an area in which we can make a sustained contribution over the coming years and decades. So we have constructed a program called the MINAR program, the Mine Analog Research Program, that brings mining and space exploration together. And we're doing this in conjunction with groups at NASA, and I'll come back to this in a second. This is actually going to be launched next week. We're going down to Boulby for 3 days to have a workshop called From Outer Space to Mining. The first 2 days will be bringing together various groups around the world to use our Bissell facility in Boulby to begin an analog program. So when I say analog, I should explain that analog research is basically using extreme environments on the Earth to test technologies for extraterrestrial exploration. So mine analog research is using extraterrestrial analog environments to improve our ability to explore space and improve mining as well. So we've got representatives coming next week from the European Space Agency, the German Space Agency, UK Space Agency, and Surrey Space Centre and NASA to begin this program. This is an open program. If anyone's interested in getting involved, please just drop us an email and we can tell you, particularly if you've got instruments to test, how we can go about doing that. This is the plan for the MINAR program. We've got 4 major objectives: test technologies of mutual benefit for mining safety, mineral exploitation and space exploration, enhance the development of technologies for the study of extreme environments, test technologies for the subsurface exploration of other worlds, and then test mission architectures for the exploration of other worlds, particularly including communications, science implementation, and mission control in an integrated way. I'll come back to that in a second. Sam Paler has already been working in the lab as a PhD student, so we've already got science going on down there, and we're going to be building on our science to build this analog research program. It's worth saying that there are lots of subsurface environments on other worlds that are very interesting and could be interesting for astrobiology. Here are just some satellite images of caves on Mars and the Moon. These are really spectacular little black dots in satellite images of the surface of Mars. This is a Martian cave. It's a few hundred meters across, and when the sun's at the right place, you can see the edge of this great cavernous entrance. This is probably a collapsed lava tube. You can find them on the Moon as well. These are interesting environments because they give you access into the subsurface. And the surface of Mars, as we've already heard, is rather inclement. It's oxidizing, it's desiccated, and it would be interesting for astrobiologists to get into the subsurface. It's technically difficult to drill in there, so one obvious way to get into the subsurface is to go into natural caverns. So we can use our Bissell facility to develop technologies for the subsurface exploration of other worlds. So let me just give you an example of how this is going to work. Later on this year, we're going to be running our first analog mission there in conjunction with our colleagues at NASA Ames. And this is a program that we've developed through our affiliate status with NAI. And this is in conjunction with Darlene Lim, who has been working over at Pavilion Lake in the Canadian Arctic, developing mission architectures for the robotic and human exploration of asteroids, Moon, and Mars. So when we started out in this, we realized there's no point in building an analog program from scratch. We might as well go to people who already have expertise. And this is the mission control, and they sit there up in Pavilion Lake and operate submersibles in Pavilion Lake to explore other planetary environments. And we're going to take that expertise and translate it to Boulby. So the idea is we'll set up a mission control on the surface of Boulby, and using the fiber optic link into the mine, we will put robots and other instruments on the end of this fiber optic link and simulate subsurface exploration of other planetary bodies, as if these things are crawling around in lava tubes on the Moon and Mars. So we've got the NASA Office of Human Spaceflight involved, Physiology and Operations at NASA Johnson, and the Intelligent Robotics Group at NASA Ames. And they're going to be represented at our meeting next week with ESA and the UK Space Agency. And over the coming years, we're going to build up this program, hopefully more and more with the kind support of CPL, and really make a contribution to analog research. But what we hope is going to spin out of this is improved technology for gas detection, mineral detection, that will be useful for the mining industry, bringing these two communities together of mining exploration and space exploration. So again, the point I want to make today is just simply say this program is getting off the ground, and if you have ideas that can contribute to this, please just get in contact and we can involve you in this. We also have another program that is being funded by STFC, GeoRepNet. This has been slightly slower to get off the ground, but we've now got a postdoc who's about to come into place in next month. And this is a continuation of this interest in deep subsurface exploration and space exploration. GeoRepNet is a network to address challenges in the establishment and maintenance of geological repositories. One of the challenges of the future is burying our waste, both nuclear waste and carbon dioxide, carbon capture and storage. And this network is to look at the overcoming the challenges of establishing geological repositories. And these are the three main challenges if you want to bury waste: locating a place to put a geological repository, building the geological repository and monitoring it. And all of these require technologies that can operate deep underground and can be used for studying the environment in which repositories are built. This is not connected with CPL because Boulby is not going to be a geological repository. But there are connections with using technology for mining and other applications for developing geological repositories. And this is going to be a 3-year program. We hope actually will carry on well beyond the core funding we have from STFC. We hope that GeoRepNet will be a long-term network run by UKCA to contribute towards the establishment of deep geological repositories. So these are some of the ways in which astrobiology can connect with solving urgent environmental problems. It's easy to get distracted by the little green men and the aliens and to think astrobiology is exciting and looks at fundamental philosophical questions but maybe doesn't have practical applications. But it very much does. It has very, very prosaic applications to some of these challenges. Okay, moving on to public education, Objective 04. Of course, doing all this science is a very good way to, astrobiology is an exciting area, as Lynn made very clear in her talk. And so it's a very good way of educating the general public in science. And about 1.5 years ago, I was invited to the Shetland Islands to give some talks to high schools there about astrobiology. And I met these students, and they were just really wonderful people, very, very enthusiastic, really keen on space exploration. But something really hit me on one of the talks I gave at the high school in Lerwick. And one of the students came up to me and said, well, this is all really interesting, this astrobiology, the Mars rovers, it's all really exciting, but it's not really for us because we don't get these opportunities here, but it's nice to know about it. And I actually thought that was a worrying thing. And I went back to Paul Bendix, who was secretary of the Shetlands Astronomy Society, and we were having lunch, and I said, we have to do something about this because people have to realize that it's not for other people. They can do this themselves. So over the last 6 months, we've set up the Astrobiology Summer Academy, and this is a joint initiative with the NASA Astrobiology Institute to launch a summer academy that will give high school students the opportunity to learn about astrobiology and to engage with this area of science. It's now been funded by the UK Space Agency and the Royal Astronomical Society, and the pilot scheme will run this year from July 7th to the 13th here in Edinburgh for a week. We've got 15 students coming from UK for the pilot scheme, 10 from the Shetlands, 4 from Edinburgh, and 1 from Leicester. So 1 from England, 14 from Scotland. It'll be a character-building exercise for them. But next year, we plan to expand this beyond 15 to many more. We're focusing on isolated and disadvantaged communities. Why are we doing that? Well, people who go to very well-resourced schools and schools in large cities sort of assume they can do astrobiology. They do their degree, they're going to go to university and do physics. Teaching them astrobiology isn't really a priority because they'll just choose to do that later in their careers when they go off and do their degrees. The problem is with isolated, when I say disadvantaged, I don't necessarily mean economically disadvantaged. I mean communities that don't have connections with space agencies or in places where it's difficult to get those connections. And so we hope to give these types of students the opportunity that they want. There's going to be a week of lectures, activities, and group work, and it's going to culminate in a student-led public astrobiology event at the Royal Botanic Gardens in Edinburgh. So this will be on Friday, July the 12th, and the students during this week will have responsibility for putting together this whole event with lectures and hands-on activities. And I want to see them stand there and look into the eyes of someone twice their age and see a sense of wonder inspired in that person, using knowledge that they didn't even have the week before. And I think once they've done that, they will realize that this isn't for other people. They can actually do this themselves. So this is a very, I think, exciting event. I want to thank all these people who have made this possible. Matt Knoll, who's course director this year, and all of these individuals here, many of them in the room, who have given their time completely voluntarily to do this. It's utterly unsustainable, but this is the way it's going to run this year. But we hope to build this up over the coming years. We've got the funding for this year, but I'll be mercenary and say we need about $50,000 a year to make this happen in the next year and beyond. So if you know of anyone with spare cash who's interested in outreach and educational outreach, or if you've got any spare cash, please send it to us, and it will be put to good use in ensuring that this is a long-term venture. The connection with NASA is that the NASA Astrobiology Institute are sending their graduates over to work with these students. So not only are they going to have the opportunity to engage with astrobiology, they're going to meet NASA graduate students and learn about working with other people and get a sense of internationalism into their lives as well, and learn about other cultures. And we hope the US students will also gain from coming here to Edinburgh. So we hope this will be a long-term connection with NASA and building up this Astrobiology Academy. One other project that we've launched, or rather Edinburgh's launched and involved us in, which has been very productive, is a Coursera course. This is an organization that runs free online courses, and you can join up at www.coursera.org. There's a huge number of courses. I don't know how many universities are now involved in this. It's something like 60, and there's about 200 courses. And we were asked to put together a course on astrobiology and the search for extraterrestrial life, which is an online course. It's one of 6 Edinburgh courses. And we put together 5 weeks of 32 lectures online, quizzes to assess the knowledge at the end of it. And the great thing is it's open to anyone, anywhere, and it's free. So if you're interested in getting an introduction to astrobiology, please take this course. If you know of anyone who's interested in astrobiology, this is a good way to learn about astrobiology. Here are just some statistics on this course. And I should point out, this is not unusual. These are typical numbers for these massive open online learning courses. We have 35,000 students enrolled in our course, over 250,000 unique viewings of our astrobiology videos, over 250,000 views of the discussion forums, and over 7,000 students saw this course through to completion and got their certificate of accomplishment. And these numbers are just staggering. And this is 100 years of my second year Properties of Matter course at the University of Edinburgh in terms of student numbers. So it's an amazing way to reach out to a very large number of students in astrobiology, and we're excited about this because in some sense it's a sort of flagship education project for our centre and a very good way for us to reach out. I trawled through all the student comments to try and come up with a summary. This I thought was just the best. There's nothing more to be said. Anyway, this will carry on running into the future, and we welcome people to take involvement in this. I just want to briefly go back to O2 before I say something about the management of this centre and then conclude. When we talk about molecules and life in extreme environments, very much our science focus is with microorganisms, because that's what we have expertise in. But it could also include humans beyond the Earth, as Lynn so eloquently summarised. And there is something that's quite interesting to us in political philosophy. If you haven't noticed, this city, in fact Scotland as well, has a long heritage of political philosophy. If you're in Edinburgh for a while, take a walk along the Royal Mile and you'll bump into the statue of Adam Smith, who wrote The Wealth of Nations, a book that's the foundations of all capitalist economics, in fact, the economics of the whole of the Western world. So it's appropriate that this is a place that also thinks about the future of political philosophy. So here's an image. It's a Japanese concept of a Mars base, and it's all very exciting. You can see things. This looks like a football stadium, but I don't think that's what it is. I think it's some sort of habitat here. There are habitats. There's a Martian wind farm here. There's a Martian aeroplane. These people are digging around, maybe doing some mineral prospecting. Yeah, it's easy to get distracted by the excitement of this image. But if you stare at this for a few minutes, you realize that what's much more interesting is what's not in this image. Okay, there are no children here playing around in the sands of Mars and learning to express their freedom and creativity. There are no adults sitting around in cafes discussing the government of the day or the economic situation on Mars. There are no government employees with placards complaining about their wages outside some government building. In fact, every single person in this building is either trapped in a pressurized habitat or in a restricted spacesuit. So it's easy to think that this is an image of human freedom, humans breaking out beyond the Earth, establishing settlements in the universe, this great free expansion of humanity into space. But in fact, this may be an image of human tyranny. And the question is, how do you sustain democracy and free government in an environment where even the oxygen you breathe is a result of a manufacturing process controlled by someone else? And this is a personal interest of mine that I've had for a number of years. And we're now pursuing this through this center. So this is the question, extraterrestrial liberty. What is freedom beyond the Earth? This is a question. What is freedom? Goes back to John Locke, Hobbes, Tom Paine, Madison, many other people who put in place the precepts of free government in the early Enlightenment and into future years. And over the next 10 years, we're going to hold a series of workshops to explore the nature of freedom beyond the Earth and the precepts of free government beyond the Earth. We have our first workshop in June, and we've collected together an interesting range of speakers to talk about freedom beyond the Earth. It's a 2-day meeting. You can still register for it if you're interested. It's on the British Interplanetary Society website, who are the organization we're working with. These essays are going to be published by Springer as essays on extraterrestrial liberty, the first volume, and they're going to publish the future workshop proceedings. And we think that this is an interesting contribution to how do humans adapt to beyond the Earth. It's a little bit of a left field activity for the center, but it provides us with an interesting philosophical and ethical contribution to astrobiology. And Lynn mentioned earlier that astrobiology does have this ethical dimension as well. If we move beyond the Earth, what does it mean for us? So this is just a point about our interests in social sciences and political philosophy, and it connects to schools of social sciences here in the university. So that's really our projects. And as I say, this is more of an advert to say that's what we've done over the last year, and we want to involve more people and get more universities involved. So please encourage anyone you know who has an interest. I just want to say something about the management of the centre, more for the benefit of my line management, to ensure that they know that we're trying to make this thing accountable, at least in some way. We have a board that runs the centre. This is actually going to be expanded over the next month to involve the School of Informatics, School of Mathematics. We have people looking at the origin of life and the mathematical basis of the origin of life. So we're doing our best to try and bring together a coherent management structure, which is what we're doing here. We have many collaborations across the UK. We've been connecting with universities in a number of places. We've got now groups interested in the origin of life and life in extremes across 15 universities across the UK who we're working with. We're also working with the Scottish Universities Physics Alliance that coordinates a lot of physics up here north of the border. So we hope that over the years we can build connections with other centres. This is important because we've had the cheek to call ourselves the UK Centre for Astrobiology. And if you're going to do that, you need to start behaving like you represent the UK. And that's what we intend to do. We call ourselves that, I should say, because NASA wanted a connection with the UK, a specific node, and we thought it was appropriate. The Spanish have a Spanish Center for Astrobiology. There's a Colombian Center for Astrobiology, Brazilian Center for Astrobiology. So it was time that the UK had a node. But having said that, if we use United Kingdom, we need to make sure that we have impartial connections with the rest of the UK, which is what we plan to do, and we plan that our facilities will make that possible. We have challenges ahead. I just want to mention a couple of those. Short-term challenge, of course, is critical mass at the moment. We have connections with other people in Edinburgh, but the driving force, of course, behind this has been my research group and my students and postdocs who have put in an enormous amount of work, I should say, also for this meeting and the conference. But if we're going to sustain a UK centre, we need to build critical mass over the longer term. Over the very long term, a building would be excellent. If anyone knows of anyone that's got £15 million spare, something like this would be great. Then we can start consolidating a real physical presence in one place. This isn't urgent, but over the next 10, 20 years, it would be good to do something of this kind. So we've got our eye on that, just so you know. And I just want to finish off my talk with a sort of vision statement. Someone asked me 3 weeks ago, why are you doing this? And they were asking it as a very personal question. You know, what's going on here? Why did you turn up at Edinburgh and want to set up a centre for astrobiology? So I thought I would just finish off with a sort of rather broad statement about the fire that's burning under this centre. This is a painting that I commissioned about 11 years ago from Marilyn Flynn, who's an astronomical artist, and it's called The Ascent of Olympus, and it depicts the first expedition team to complete an unsupported assault on Olympus Mons, which is the highest mountain in the solar system. It towers about 2.5 times the height of Mount Everest. This is a very auspicious day in the history of human exploration. Hillary and Tenzing have just been eclipsed, and this is a new era in human mountaineering. It's a sort of fun image because it's based on real satellite imagery. When I asked Marilyn to paint this, I sent her the satellite images of the Olympus caldera, the top of this spectacular extinct shield volcano. So you're actually looking north-northeast across the mountain. This is based on Mars orbital laser altimeter data. So this is the highest point. This probably isn't real here, but this is a real vista. You could go up here in about 100 years' time and recreate this picture. And what I think is fun about this is we don't know who these people are. We don't know what nationality they are. But we know exactly what's running through their minds, and we know what's important to them and what's not important to them. For example, we know that they're not thinking about the REF 2014. We know that they don't care who won the Student Satisfaction Survey in 2016. And we know they don't mind, you know, who was elected to this or that society or who won this or that award. None of these things are important to them. And I'm not belittling these things, but they're just not important with a capital I. What is important to these people, and what they do care about, is the fact that in the early years of the 21st century, there were individuals and university centres who set their minds on contributing towards establishing a permanent human presence beyond the Earth. And we know that's important to them because otherwise they couldn't be standing at the summit of this mountain in the first place. And that's really what the UK Centre for Astrobiology is about. I mean, that's the fire that burns under this centre. We want to contribute towards the science, the technology, and the education that enables astrobiology to improve our understanding of our place in the universe and ultimately to allow humans to move beyond the Earth and establish a presence beyond the Earth. So I think in summary, what I would just like to say is that these are the projects and plans that we have over the last year. We're still a very young centre, still very fragile. It's easy for something like this to fold. And it depends upon the goodwill and the support of the community. So we'd like to invite your support and invite your involvement in our projects, if any of these have been of any interest. And above all, I would like to thank you for taking the time to come to our opening and see what we're about and what we're planning to do. And on that note, I would like to finally hand over to the head of the School of Physics and Astronomy, who has been very patient with us and our plans since I arrived at Edinburgh in allowing us to just get on with this. And I should say more than that, actually, providing funding for our Mars simulation activities. So if I could ask Arthur True to say some final words. Arthur.
Ladies and gentlemen, as has been pointed out on quite a few occasions, astrobiology is an interdisciplinary science which crosses many different traditional areas, but it's my privilege as head of School of Physics and Astronomy to have Charles in the UKCA within physics. And it's also my privilege, I have to say, to be head of school at a time when physics has been more exciting than it's been for a century. Some of the problems that generate that incredible excitement we've known about for, let's say, 30 years. And today we can do experiments such as the AMS detector that's been up on the International Space Station for the last couple of years, looking for signs of the dark matter that the astronomers first found from observational data in the 1970s. Some of the problems that create the excitement we've known about for 50 years. We've known for decades that the two fundamental theories on which physics is built. General relativity describing gravity and the universe at large, the standard model of particle physics describing the very small and the universe on the very shortest timescales are incompatible. Today, we're doing experiments at the Large Hadron Collider at CERN that might probe some of the reasons why there are these two theories that just won't fit together and try to let us look beyond that. But as already has been pointed out by two of the speakers, and this is one of the problems of coming relatively late in the day, you lose all your best lines. Some of the problems date back very much further. They go back to a time when man first stood and looked up at the night sky and said, are there other suns like this one? Are there other Earths like this one? Is there more life out there? And those sorts of problems, until relatively recently, became they were effectively unscientific. We couldn't experiment on them, and yet today there are observations that have found something in the order of 1,000 exoplanets. Perhaps the recent results will double that number. But just over the last few years, we have evidence for enormous numbers of these things. And extrapolating on the 1,000 exoplanets that we have found to date, the estimate is that there could be as many as 4.5 billion planets within the galaxy. So, of course, not all of these planets are going to sit in the so-called Goldilocks zone, where we have just the right amount of heat that water doesn't freeze and just not so much that it doesn't boil off into space. But many of them will. And that gives a real opportunity for us to speculate on what life would be like on those other worlds. When Charles was appointed to the chair of astrobiology at Edinburgh just 2 years ago, seems much longer in many respects, I thought this was a really sort of promising, higher, interesting new area for us. What I didn't envisage was that we'd be standing here today inaugurating UKCA. The astrobiology activity which he has nucleated and really pushed forward has been incredible for us at Edinburgh. It's gone beyond the simple observations using WASP or what have you, finding that there are indeed planets out there. It's actually taken us to that next level and let us have a look at what might be life might be like on those other Earths, looking at the behavior of molecules, if you like, in these extreme conditions at Earth. And the linkages that, for me, were a revelation that he has opened up are ones that, for example, underground experiments at Boulby can actually tell you something about life on the surface of Mars. That's a leap that had to be explained, I have to say. The UK Centre for Astrobiology is a nationwide collaboration. It spans the UK. It's affiliated to NASA. And I must say that if as a 10-year-old boy, and that's the age that I first became interested in astronomy, I thought that I would be able to stand here today and talk about our links to NASA, talk about the search for life on other planets, talk about the fact that only a few miles south of here we have a simulator that can reproduce conditions on the surface of Mars. I would have been completely overwhelmed. Here today, just a few years later, I'm thrilled by the opportunities for interdisciplinary research that UKCA has produced for us. And so for Charles, for the board of UKCA, for his researchers, and for all of the associated universities, I just want to wish you all the best for the future, and I know it will be a tremendously successful program. So congratulations for what you've done so far, and all the best for the next decade or two. Thank you.
This production is brought to you by the University of Edinburgh.